So let us go back to our discussion on special relativity and revise for the time being. So we said in special relativity we have this concept of interval, or we call it space-time distance or metric, which is the essentially the space-time distance between two events E1 and E2, and that is given this way. When I write in terms of Cartesian spatial coordinates, but I can also write in terms of polar coordinates, where it comes out to be what is written over here. And then we said we will consider only radial trajectories, where d phi and d theta becomes 0, and we get ds squared like this. We then discussed about space-time diagrams. One event is a point in this diagram. Trajectory of or one line of a particle at r equals to r0 and doesn't move with velocity 0 looks like this, and then one line of a particle with velocity v looks like this. Then we figured out that the angle that this thing makes for a one line of a particle with velocity with velocity v, that angle tangent of that angle is given by c by v, where c is basically the speed of light. And if I consider a radial light ray, then the velocity is also c, so tan theta becomes 1, theta becomes 45 degrees, and ds square is 0. So we got that fact that the radial light rays c square dt square equals dr square. Now the rest of the discussion will use radial light rays in two particular cases. Okay, so what we are doing now is consider that, let's do a thought experiment. So these are critical to all relativities. So let me tell you what is the experiment. So to do that, I draw this space-time diagram with, as always, x-axis as r, y-axis as ct. And I have two stationary observers here. I have one observer at r equals to r1, the other observer is at r equals to r2. Okay, and they're stationary observer, and as we have discussed, their world lines will look like this. So this is the world line of the two stationary observers. So what are they doing? So what the observer 1 does is that the observer 1 sends light pulses. So observer 1 sends light pulses at regular interval. So you can think of like he is sending. So let me just draw for you one example of what he's doing. So if this is my time axis, he's sending, say, this axis is now amplitude and this is time. So he is sending, for example, a sinusoidal wave, maybe a sinusoidal electromagnetic wave. Light pulses, so it has to be electromagnetic wave. Okay. Remember, this is amplitude, this is not distance. What does observer 2 does? Observer 2 receives. Observer 2 or receives, observer 2 receives the light pulses sent by observer 1. Okay. So say for example, the first light pulse was sent by observer 1 at this time. I say in this continuous thing, but I am only looking at the highest amplitude ones, and the second one was sent at this time. Okay, so let's look at the first light pulse. So the first light pulse starts here. So let us call this time t emitted. What trajectory will it follow? A 45-degree line. It gets observed here, and the time, say, let us call that t observed. So the first pulse receives the observer 2 at t observed. The observer 1 sends the second pulse, or the position of the second maxima is at t emitted plus delta t emitted, and that pulse start traveling from there with a 45-degree world line and reaches there at observer 1, observer 2 at t observed plus delta t observed. The light takes some time to go from there to there. Because of that, obviously, they will not be received exactly at the same time. Right? So, I'll link this space. So, let me write thought experiment in a little different way. I write it this way. Fine. So, these are what observer 1 and observer 2 are doing. So, let me draw the timeline over here once again and mark this 4 events, 4 times. So, this 1, this is 1, this is 1, this is 1. So, t emitted plus delta t emitted, t observed plus delta t observed. Fine. So let us ask the question, how much time it takes for the light ray emitted at TE to reach observer 2. Okay, looks like a very trivial question, but we will follow a particular way of answering this, and that's why I have take up this. Okay, looks like a very trivial question, and shortly we'll see not always this will be so trivial. Okay, so this will not only ask for the emitted at t emitted and observed at 2, will ask for both the light rays. And let's see how to answer this question. Well, we know that c square dt square minus dr square is 0, and anybody a little clever can say that dt which is the time difference, is given by dr by c. Okay. So for light ray 1, so let us call these light rays as light ray A and light ray B. Okay. So the first light ray emitted at T emitted, observed at T observed is A, and the other one is B. So light ray A. Light ray A, I just have to integrate this expression. How do I integrate this expression? Well, let me write the right hand side in the left hand side. So for light ray A, I have this dr by c equals dt. There is a reason I am writing dt a little far away, but it's just the same equation. And this integration is from R1 to R2. So the light ray starts from the observer at R1 and goes to the observer at R2. And here the integration is, it starts at the time t emitted and ends at the time t observed. So that is essentially, if I do this integral, obviously I will get things for the first light ray. But let's not do the integral straight away. Let's look at the light ray 2 or light ray B. For the light ray B, again it emits at position R1 and received at position R2. So the left hand side of the integral doesn't change. The right hand side, though, there are different things, because it's emitted at T emitted plus delta T emitted and observed at T observed plus delta T observed, right? And you obviously have the integral over dt. This integral I want to break down. So let's see what is the limit of this integral in this timeline diagram. The limit is from observed, emitted to observed. So this is the limit. So these are the two ends of the limit. So lower limit is T emitted plus delta T emitted. The upper limit is T observed plus delta T observed. This I can write as this integral with a lower limit T emitted to upper limit T observed plus this integral. So let me write the first one first. So the first one I will write T emitted to T observed. So here I will write the integral from T emitted to T observed dt plus, what should I add? So I can add this much, which is T observed to T observed plus delta T observed. So let's add that. T observed to T observed plus delta T observed and dt obviously. But if I do that, I have now taken an integral from here to there. But in the original integral, this much is missing. So now I have to subtract this integral, which is T emitted to delta T emitted. So let's do that. Minus T emitted to T emitted plus delta T emitted. Now this is half of the crack of the story. So let us go through it again. We wanted to do this integral for the light ray B. To do that, what I did is I first took this part, then added this part, so I get from here to there, but then subtract this part, so then I get back this integral. So that's essentially what I have written down here. If we subtract now this line minus this line, if I do, the left hand side becomes 0. In the right hand side, the first integral is same, so that cancels out. So I'm left with t observed to t observed plus delta t observed dt minus t emitted to t emitted plus delta t emitted dt. Let's do that integral. That integral is straightforward to do because this is just an integral over t dt. There is nothing constant times dt, so it will be t. So this integral will be t0 plus delta t0 minus t0. This integral will be minus of te plus delta te. Let me put it with a bracket, minus of te plus delta te minus te, which is equals to 0, and you immediately see that t0 cancels out, te cancels out, and this minus that is essentially means that delta t observed is nothing but delta t emitted. Such a wonderful result, and there is no surprise in that, just because we are essentially saying what is being observed here, the time interval between the two successive maxima of an electromagnetic wave, sinusoidal electromagnetic wave, is exactly same for the observer 2 as for the observer 1. So this I can translate to, so this is the time difference between the two successive maxima of the electromagnetic wave, and that is nothing but, so this time difference is nothing but the time period of the wave, right? So the time period of the wave for the observer 2 is the time period of the wave for the observer 1. Okay, that is obvious, but you will see that it is not so obvious shortly. It is not what happens in case of cosmology. In fact, you can imagine that what R2 is an observer on Earth, and what R1 is a galaxy. And this is the spectral line, this is the electromagnetic wave of the spectral line, this is the electromagnetic wave of the spectral line emitted by the galaxy, and it's received at R2 at the Earth. And in this particular scenario, we will not see any redshift or blue shift. We will just see that their time periods, and hence obviously if the time period is same, the wavelengths will also be same. If you not so let me remind you the relationship between time period and wavelength. So time period goes as or equals to, actually, so time period is equals to 1 by frequency, which is equals to lambda by c, right? Sorry for that noise. So time period is equals to lambda by c, which means t0 equals te essentially means lambda 0 equals lambda e. If you remember that the redshift is nothing but lambda 0 minus lambda e by lambda e. If lambda 0 equals lambda e, redshift is 0. Right? So this is what we have seen for this particular example. So this was the case for special relativity. And it obviously doesn't explain Hubble's observation. Now let us come to cosmology. Okay. And people were very, very good in doing science, I would say, even at the time of Hubble, because they did this amazing postulate. They said that we should start by explaining the universe, assuming that the universe is homogeneous and isotropic. This is called the cosmological principle. What do I mean by the word homogeneous? It means that universe looks the same with respect to any place. Neat. So wherever you are in the universe, if you look around, you will see the universe exactly the same. Or if you think of, instead of being at the planet Earth in the solar system, which resides in the galaxy called Milky Way, if you would have done the Hubble's experiment from any other galaxies in the universe, from any other star systems, from any other planets, you would have come to the same conclusion as Hubble did. So that's called the homogeneity of the universe. And that's a very bold assumption. It's throw away the fact that we have anything special to do with the universe. We are just one place in the universe. What is isotropy? It means that all directions are same. So whatever direction you look at and do the Hubble's observation, so if you divide your celestial hemisphere to different right ascension and declination regions and do the Hubble's observation, you will again find the same Hubble's law. It does not care about which direction you are looking at. And we have kind of used that already because we are considering only radial light rays. We are even not talking about theta and phi, but anyway, so these are the two assumptions that the cosmological principle takes, that universe is homogeneous and isotropic in any direction you look at. Then it asks the question, then it asks the following question: what is the most general metric when the spatial part is homogeneous and isotropic? So that is the question that people asked. What is the most general form of a metric when the spatial part is homogeneous and isotropic? Remember that we wrote down a particular metric which we called comes from the spatial relativity. So this is the metric written for the spatial relativity in Cartesian spatial coordinates. There is the same thing in the polar spatial coordinates, and we did not give any reason to write down this metric. There is a way to derive this metric for spatial relativity, but here we are not asking that question. We are asking the question that if I just take this assumption that the universe is homogeneous and isotropic, and I don't take any other assumption, what is the most general metric that one can write down? Now this has the relation with what we call the general relativity. And obviously I will not be able to tell you much about general relativity here. I will rather talk to you about what is the difference between spatial and the general theory, why it is called spatial and why it is called general. Well, spatial relativity is called spatial because it uses the following way of doing physics. So idea of doing physics, or idea to solve trajectories of particles, came about in the following way. People said that they'll first figure out the equation of motion of these trajectories in a given reference system. Okay. And how do you do that? You use Newton's laws of motion, or say the laws of electrodynamics, the Maxwell's equations, the Lorentz force law, which is a charged particle. You use these things to figure out how to write down the force, or how to write down the trajectory of a particle in a given reference system. But all the observers are not in that given reference system. So what do? You have another set of rules which tells you that if I have written down the laws of physics in one reference system, how do I get the laws of physics in all other reference systems? Now, in the realm of special relativity, or in the realm of all physics before general relativity was discovered, this could be done for only inertial reference systems, or the reference systems which only moves about themselves with a constant speed, constant velocity. And because it could be done only for the inertial reference system, the name is spatial. For general relativity, it can be done for all reference systems. So you have figured out a way of finding the trajectory of particles in all reference systems once you know it for one reference system. So that is the magic of general relativity. How do you find the trajectory? And the first part of that is to write down the metric, or the distance function ds squared. And if I have a universe which looks the same with respect to any spatial, any place in it, and looks the same if you look at all directions, which is the universe is homogeneous and isotropic, then I can ask the question, what will be the most general form of this metric? And that comes out to be the following. Well, so I'll not write down the most general form. I'll write down a little more specific form which we believe our universe obeys today. So this metric is called Friedman, Robertson, Walker, Lemaitre metric. FLRW, FRWL, whatever way you can add the name of these people. And I am assuming the spatial part is flat. I'll not go into a very large discussion on what is the meaning of that. If you wish to know, you can drop me a question in the class comment section, and then I will explain to you. Otherwise, I'll just say that we are considering a spatially flat FLRW or FRWL metric. And that metric looks like this. The only difference here, this metric with the previous one that we wrote down, is this quantity a square t. Everything else is as it is. Okay. So what this a square t does? So first of all, you realize that this is a time dependent factor. Secondly, what it does is it scales the spatial distances. Right? So what I have written in the square bracket here is the spatial distance between 2 points, as we have discussed earlier also. This only scales the spatial distance between 2 points differently with different times. So this is called a scale factor. So AT is called the scale factor just because of the fact that it scales the distance between spatial points differently at different times. Okay. So this is the FRLW or Friedmann-Russell-Lemaitre-Walker metric, and this is the metric one should use to understand the propagation of light rays, radial light rays in the universe. One more thing about the scale factor is the fact that I can choose my definition of the distance whatever I choose. So what I called 1 kiloparsec or 1 megaparsec distance definition is up to me. So I choose AT such a way that AT at present is equals 1. Okay. So if I measure the distances of my nearby objects at present, then I can just use the old special relativity metric. If I have to think about light rays coming from very far away from the universe, then I have to include this. Why should I include that? Let us go back to our space-time diagram of the propagation of two light rays. Okay, so this is the space-time diagram of the propagation of two light rays. You see, according to the FLRW metric, the scale factor changes as you go up in this diagram, because time changes, the scale factor changes this way. Right? Which means the scale factor here, when the observer 2 receives the signal, is different than the scale factor here. Obviously, if they are very close by, light doesn't take much time to go from there to there, and the scale factor you can consider roughly be the same. But if they are quite far away, if this distance is say 1000 megaparsec, then obviously the scale factor, the light will take a long time to go on 1000 megaparsec. You can calculate the time, how much time you should calculate, how much time it will take to go 1000 megaparsec. By that time, the scale factor will change. So for nearby calculations, I can neglect the scale factor, just saying that it is equals to 1. But for the calculations where I have the galaxies far apart, just like for the Hubble's observation, I have to consider the fact that the scale factor changes with time. So for the nearby calculations, I can take AT0 equals to 1. For calculations far away, I cannot take it. Now, given the FLRW metric, what is, so if, and I take radial light rays, again, what will I get? dA square equals 0, means light rays, d theta and d phi also 0, means radial, and this essentially means that AT dr is nothing but c dt. And if I want to calculate the time difference just like before, now I just not be able to integrate over just AT. I have 1 by AT times dt, right? So let me write it in more proper form. So I just, so I get, I'm writing the exactly same thing, but in just a little bit better way. So dt, not dt, dr by c is nothing but dt by AT. So that is the formula I should use now for the radial light rays. Remember, in the previous case when we used this special relativity metric, this formula was this, where I did not have the divided by AT over here. Okay, so let's see how things will proceed from this calculation. The only thing that will change is everywhere I have dt there. So let me just okay, yeah. So I think I can take this part of the calculation and carry it over there. Just a second, let me try it again. Something's happening. Okay. Nice. So this is the previous calculation. Now let's see what change we have to make here. So we have to make the change that wherever I have dt, I have to put a divided by a over t. So that's coming from there. So let's do that everywhere. Which brings us to the fact that this and now you can see obviously we have done this calculation once, so I can just manipulate it a little bit here and can write this equals to that. Now this, as I said, the scale factor doesn't change very fast, so by the time you send the second emission, second peak of the electromagnetic wave, so remember, so let me go back to that picture once more because probably that will be handy for you. So in this picture, you see that this is where I have one of the maxima of the electromagnetic wave, and this is the other maxima. And by the time this happens, so this is kind of happening it. So if it is a light wave, the frequency of the light wave is 10 to the 14 hertz. So this is happening 10 to the 14 times, 1 by 10 to the minus 14 second between this time interval. The universe doesn't change by that time. The AT is not changing by that time. That you can imagine. So in that case, I can assume that when I'm doing this integral, this AT can come out of the integral, but I have to consider the value of AT at t equals to t0 here. So this I can write at 1 by a t equals t0, and then the integral from t0 to t0 plus delta t0 dt, and that is equals to, and when this comes out, that will be a te. Right? Now, as we said, that T0 corresponds to the observer 2 in our case, and the observer 2 for Hubble's observation is Hubble himself, which corresponds to the present time. Well, Hubble did the observations maybe 100 years ago, but in 100 years again is very small time for the evolution of the universe. So universe, as we learn in the next few classes, is 13.6 billion years old, 10 to the 13.6 billion years. So 100 years is nothing in that 13.6 billion years. So this is essentially 1. So AT observed, that we have just said that we will consider AT observed, AT0, which is the present time, which is AT observed here, is 1. And this I can just say at ATE. So that's a time. That's A as a time t. So what will I get then? So this is 1. This integral we have done before will give me delta t0. And this integral we have done before will give me delta t emitted. Right? So this is the result of doing the same exercise that we did before, that experiment, with the FLRW metric now. So I have this extra factor over here. And as a consequence, delta t0 is nothing but the observed time period of the same electromagnetic wave is now the time period when the electromagnetic wave was emitted by ATE. Similarly, if I write the same thing in terms of lambda, so this is lambda 0 by C equals lambda E by C 1 by ATE. Or let me come to the conclusion directly. C I can cancel out, so I get lambda 0 equals lambda observed, that is lambda observed equals lambda emitted by AT. ATE, I am just writing AT because that is the time at which it was emitted. So what is the redshift Z? Redshift is lambda observed minus lambda emitted by lambda emitted. So I get Z equals, so what is lambda observed? Lambda observed is lambda emitted by AT minus lambda emitted by lambda emitted. So lambda emitted cancels out from everywhere, I get 1 by A minus 1. Or you can write the same thing in a little different way. This is a formula that we'll use again and again in cosmology. Okay, so it's the relation between the scale factor, which comes from, so what is the origin of the scale factor? So let me write this relation again and tell you why it is important for cosmology. This comes from metric. So it's a part of the theory which is the theory of the modern cosmology. This comes from observation. So in a way, that this is a relation which is relating your theory with the observation. So that's why it is so important relation in modern cosmology. Nice. So we have to discuss one more thing before we call it a day today, before we end today's discussion, and that is related to the fact that all we have done so far is all right, but what is the relation of all this with Hubble's law? And to do that, I come back to this expression again. So let me write it here. This is essentially the entire FLRW metric. So this, when I write this as vector r, this is nothing but dr square plus r square d theta square plus r square sine square theta d phi square. Okay. This entire thing is the scaled distance. Right? So this distance will be different. This is different at different t. This has a name called proper distance. Often this is what you measure. So this is proper distance dp. And what is it equals to? It's equals to at. So when I say distance, scale distance, I obviously mean the square root of this. Remember, this is distance square times this dr. Well, so I am again, so when I am writing this, I am assuming that I have already taken the I've done the integration. So from dr I have gone to a length instead of an infinitesimal length, and that I called dc. So this is a distance, does not change with time. So imagine that you have the FLRW metric today, and you measure a dc, the distance that doesn't change with time. So dc is nothing but the integration of dr over some r1 to r2 at a given time in the universe. So you are just measuring the local distances. If you do the same exercise 1 billion years ago, you would have got the exact same distance. Why is it so? Just because we have assumed that at equals to 1, whenever you are doing the measurement. So at the time you are doing the measurement, always at equals to 1, which means at that time the measurement that you will get is just equals dc. So this distance doesn't change with time. This has a name. It's called co-moving distance. So let me highlight these out. So this is not a very good color for highlighting. Let me highlight this. It's co-moving distance, and this is the proper distance. Okay. And in between these two lies the scale factor. In between these two lies the scale factor. It, right? You see, when we discussed our experiment, it's interesting that these two observers doesn't move. They always stays where they are. Their positions remains fixed R1 and R2. They're not moving. R1 is not moving with respect to R2. It's very important because the velocity of this observer with respect to this observer in terms of the coordinate R is 0. And that's what I mean when I say that the co-moving distance between these two observers doesn't change. So dc here is nothing but R2 minus R1, which is the result of this integration, which is R2 minus R1. So this is equals, this is equals R2 minus R1 by C. So R2 minus R1 is nothing but the co-moving distance. So I can write dc by C. Right? So what is that I have got from the FRWL metric? I have got that the proper distance is equals a function of time times dc. So if I now take a time derivative of these in the both side, then obviously there will be no time derivative of dc because the co-moving distance doesn't change. So I'll get a dot, which is the time derivative of a times dc. The left hand side I can interpret as a velocity which I call proper velocity. So in some way I change my redshift to velocity. Some way I change my redshift to velocity. Then I will infer this velocity as the velocity that I get after changing redshift to velocity. So this is the velocity that Hubble inferred. In the right hand side, I do a trick. I do a dot, I divide it by a, and obviously I have got 1a in the denominator extra, so I have to multiply this by a again. So I get this, which means I get Vp equals a dot by a times a dc. That a dc is nothing but dp. And a dot by a, then, if you remember Hubble's law, so remember Hubble's law, so a dot by a, which comes here, is nothing but h naught. So that is again another observable. That one can measure out of the Hubble's law, out of the observation like Hubble, and it is related. So what is related to time dependence of A, of the scale factor A. Okay. So this is an observable H naught is related to the time dependence of the scale factor A, and you see that that is the time dependence of the scale factor A, which is the only unknown in this FRWL metric. Everything else is known, so this is a very known thing, and there is no function over here. It's just a spherical polar line element. C square dt square is obvious, C is known. So this S square is the only only function which is unknown, and that can come from observations like Hubble. So this is how the FRWL metric explains Hubble's law, and you will be able to figure out what is AP from there. Okay, so that's it for today. So what we have learned is the Hubble's observation and Hubble's law, and we will use the FRWL metric to understand more about the universe in the upcoming classes. Thank you for today. If you have any question, please keep it in the comment section as you always do, and we will take those on.